Welcome to The Explainer. Today, we're diving into something incredibly fascinating. We are merging the high-tech, precision-driven world of manufacturing right into the dirt and mud reality of global agriculture. We're going to look at how leading researchers are literally turning plant breeding into a highly optimized industrial process. Okay, so let's just dive right into this. What exactly does a car factory have to do with the food on your plate? It sounds like kind of an odd question, right? But the answer holds the key to solving a massive vulnerability in our global food supply. Look, when you think of a car factory, you think of exact specs, rigid quality control, and constant measurable improvements. When you think of farming, you probably just think of nature running its course. But here's the truth. To feed a rapidly growing global population, especially with climate change breathing down our necks, the biological processes behind our food desperately need the rigorous precision of an assembly line. Because for a really long time, the way we've developed better crops has been surprisingly, well, fragile. Traditionally, plant breeding schemes have been inherited almost like family recipes. They were passed down verbally and practically from one lead breeder to the next. You'd literally have a new breeder overlap with an older one for years just to learn the ropes. But as researchers are now realizing, this heavy reliance on verbal handoffs inevitably leads to lost data, lost germplasm, and just a highly inefficient use of critical resources. So we're basically comparing the old artisanal approach of plant breeding with a completely new industrial process, one that treats crop traits exactly like product manufacturing. That artisanal way, it relies heavily on the intuition and memory of individual scientists. It's treating vital global crops almost like grandma's secret sourdough starter. It's an art form. The industrial way, on the other hand, is completely formalized. It's software-tracked, quantifiable, and constantly subject to review. It guarantees that the development of a better, stronger crop isn't just some happy accident, but the guaranteed output of a finely tuned machine.
To really understand how we industrialize this whole thing, we first need to define what a breeding scheme actually is. Basically, it's the blueprint. It's the collection of crossing, evaluation, and selection decisions a breeder makes to create a better crop. It involves very specific questions, like how many parent plants do we use? How many locations are we testing them in? What percentage of the offspring do we actually keep? These decisions are essentially the individual gears turning inside our agricultural factory.
Because you don't just plant a seed and, hope for the best. You start with product design, mapping out exactly what the market needs. Then you move into the engineering phase. This is where you actually cross the plants, evaluate the traits, and make your selections. And finally, you hit product delivery. It's a continuous loop of improvement. Literally, the exact same way a tech company develops the newest smartphone. So, the absolutely crucial point here is how we optimize this factory. And that's where the famous Six Sigma continuous improvement method, specifically the DMAIC steps, comes into play. Originally developed by Motorola back in the 80s to eliminate defects in electronics, DMAIC stands for Define, Measure, Analyze, Improve, and Control. The researchers took this exact corporate framework and slapped it onto plant breeding. But instead of eliminating defects in a microchip, they're eliminating inefficiencies in genetic gain, which is really just the amount of measurable improvement a crop makes from one generation to the next. By applying these steps, breeders can spot bottlenecks and scientifically enhance their crossing and selection decisions, just like an automotive engineer would refine a car part. Here's how that translates. First, you define the problem. Let's say slow crop improvement. Then you measure every single decision made in the breeding scheme. You analyze that data using quantitative genetics, you improve the process through computer simulation, and finally, you implement a control plan to make sure those improvements actually stick. But hey, before you can improve a product, you've got to know exactly who you're making it for, right? You wouldn't build a massive gas-guzzling pickup truck for a market that only wants compact electric city cars. In agriculture, this is where we define our market segment. It isn't just about geography. It encompasses the environment, the specific client's needs, and the very specific product traits valued by the people actually growing and eating the food. And global market opportunities dictate the exact product profiles that a local breeding pipeline absolutely must hit. Think of it as a top-down flow. At the top, you have the what, the market segment and the desired product profile, down to hyper-specific features like disease resistance or even texture. And below that, you have the how, the actual breeding pipeline making the investment to hit those exact targets. Every single action the breeders take has to be tied directly back to an end user's requirement. To make this a bit more tangible, let's look at a real-world case study from the International Institute of Tropical Agriculture, or IITA, in Uganda, focusing on optimizing East African cassava.
Now, cassava is a massive staple crop, but improving it has historically been painfully slow. So the breeding team there decided to apply this whole Six Sigma industrial approach to their pipeline to see if they could increase their crop's genetic gain without spending a single extra penny.
Using a new piece of software called the Breeding Pipeline Manager, or BPM, the team quantified their exact targets. They weren't just vaguely trying to make quote-unquote better cassava. No, they formalized their profiles to create late maturity, hard cassava that is highly resistant to cassava mosaic disease, specifically tailored for the fresh and high-quality flower markets in lowland, high-rainfall areas. The software literally takes all that artisanal intuition out of the equation and puts hard, cold data right in front of the team.
Now, the baseline data they logged is just fascinating. To fill their fields, they were originally only using 4 parent plants. From those 4 parents, they made 12 crosses, generating 136 progeny per cross. If you do the math, that resulted in a total of 1,632 individual plants that they had to evaluate in the nursery. That 1,632 number, that is their absolute capacity limit. It's the max number of plants they have the budget and physical space to grow and test. So here's the big question the researchers asked. If we treat these 1,632 plants as our rigid factory capacity constraint, what happens if we change the mix of parents and crosses? Like, what if instead of 4 parents, we use 8 or 32 or even 64? To find out, they didn't waste years of their lives planting all these variations in the dirt. Instead, they turned to advanced stochastic genetic simulations to essentially predict the future. They mapped out all their evaluation decisions into the BPM software's flowchart and ran thousands of simulated breeding cycles using a program called AlphaSimR. They simulated a hypothetical cassava genome and basically hit fast forward, predicting which exact combinations of parents and crosses would yield the absolute highest genetic gain over massive 20 and 60-year horizons. They were looking for the absolute most efficient way to run their factory floor. And out of 24 different simulated treatments, the data revealed a perfect Goldilocks solution. Using only 4 parents, that was way too few to sustain long-term genetic diversity. But using 64 parents completely diluted the quality. The sweet spot was right there in the middle. The simulation proved that using 15 to 30 parents to make 40 crosses, yielding 40 progeny each, drastically boosts the genetic quality of the cassava. The total number of plants evaluated is still right around that 1632 limit, which means they unlocked massive improvements without spending an extra dime. As the researchers noted, they expect this generalized framework to really assist plant breeding professionals in transitioning toward conducting breeding as an industrial process. And honestly, this proves that adopting industrial optimization and genetic simulations isn't just some academic exercise in spreadsheets. By treating the farm like a factory floor, applying Six Sigma, and tracking every single decision, breeding programs can finally stop relying on guesswork. Ultimately, it's about transitioning to a highly controlled process to actually deliver better, more resilient products to farmers and consumers all around the globe.
And as climate change continues to challenge our global food systems with unpredictable weather and nasty new diseases, we are going to need our crops to adapt faster than ever before. So we really have to ask ourselves, if we can use software and engineering principles to so drastically improve the humble cassava root, what other vital biological processes can we save by thinking like an engineer? Thanks so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.